Hi everyone, thank you for coming to this presentation. I'm Mustafa Koray from SINTEF, Department of Smart Sensor Systems, and with Omid Fatimi from University of Tehran, we have done this research as a SASIAF, a scalable accelerator for seismic imaging on Amazon AWS FPGAs. Outline of my presentation is first I start with seismic imaging and then data flow computing, and then we have a look at recent hardware opportunities in the market and AWS F1 Instances and varieties from Xilinx. Related works, SASIAF Accelerator architecture, that is this paper, and experimental setup, performance comparison, and conclusion. Seismic imaging is one of the most data-intensive and computing-intensive applications in oil and gas industry. And a part of this is RTM, reverse time migration, that works based on solving the wave equations. We finally want to solve this equation in time and distance from the surface. And to do this, the procedure of each shot of the time needs to be divided in 3 forward, backward, and correlations, like this. So we need to solve these equations in PC with numerical methods. And this algorithm is combining of 3 different steps that we want to do. We get a seismic image that is in 2D domain, is a matrix with block lengths, and then we need to one time run forward computation on it, then backward computation that is from the wave that's coming from the earth to the surface, and finally cross correlate the forward and backward computations together. As you see here, these processings are related together somehow. They should be done after each other sequentially. But in each step, we have lots of parallelism embedded there. And in each of these steps, we have this stencil course. That means that for computing each point in the center of this square, you need to have access to all the cross points around it. But why data flow computing? Data flow computing is implementing instruction in hardware. Maybe the main difference between this and traditional computing with CPUs is this one. So we control the data flow by host processor, another processor that is beside the accelerator, and then use DMA between hardware, accelerator, and DDR3 memory to feed and get the data to and from this accelerator. For example, if you want to solve this, to calculate this simple expression here, z equal a multiply x plus b multiply y minus x multiply y divided by 5, then we can implement it by several building blocks from multiplication and others, and give the data in the beginning and finally have the results. With this kind of implementation, you can have only few clocks between giving data and get the results. But if you want to do it in normal CPU, you need to have, for each of these operations, you need to have load operand, load instruction, save, execute, and save it back. So it is, even if you run it at lower frequency, probably you get better result with this, and it is the motivation for implementing lots of applications and algorithms on hardware with data flow computing. But for data flow computing, there are different ways for implementation. We can start from CPUs, go to GPUs, FPGAs, and finally ASICs. CPUs on data flow computing are so limited because they have their own architectures, and you cannot change it, and the data flow needs to be designed for each specific application. GPUs are similar to CPUs, but FPGAs and ASICs are different. On ASICs, you can implement whatever you want, but it will be only for one application. And if your application is not an application that you want to sell it worldwide, and your customers are limited numbers, then it is not commercially not a good choice. But FPGAs is somehow between CPU, GPUs, and ASICs. You can implement your own hardware, but still it's affordable, and you don't need to spend so much money. However, the problem with FPGAs is development and implementation, that we talk about it later. Recently, we have several hardware options available that were not before in the market, like standard Xilinx cards, standard Intel Ultra cards, and several third parties that came and made cards based on Xilinx and Intel. Before if we wanted to accelerate an application, we had to use specific hardware and software from same company. But now we can use a hardware from, for example, Bitware, but use VITIS from Xilinx, and that's a very good combination. Also, now Xilinx and Intel, they have their own hardwares available, and we can buy them from different stores. But AWS F1 instances that we used, used it to accelerate our system and do our research. Why we use this? The first thing is that they are computing on demand, so we can use it whenever we want. We don't need to have all of this expensive hardware, like Alvo cards, that it can, the similar card that is available on F1 can be in the range of 15 to 20,000 US dollars, so they are quite expensive. And they are easy to use. We have Amazon image for them that can make it up and running in few minutes, and no need for starting investment. That's very good for research projects. Less maintenance costs, because you can just ask application engineers to help you during development, and standard hardware that if you use them to implement and accelerate your application, and then you want to have it on your own data center or somewhere else, not on Amazon, you are free to do it because you have used standard Xilinx hardware for it. Related works on seismic imaging acceleration. There are many works that have been done before on FPGAs, but most of them, as we found, were based on custom hardware, like this one that I brought it here from Maxler company, that they got very good performance, 112x performance with 4 FPGAs. But the problem is that it was based on Maxler data flow engines that forced developers to use Maxler Java compiler and then limit everything. But when we switch to more standard systems like AWS F1, then we have this option to use standard hardware, and also the IDE from the FPGA vendor that is more robust, and we can continue with it for more years. SASIAF accelerator architecture that we presented in this paper is a combination of 3 different levels. At the bottom we have FPGA level that is the bit stream that will be implemented in each FPGA to process the data. in the middle we have host level. The host level is this part of software on each computer, host computer on Amazon cloud, that controls its own FPGA cards that can be from 1 to 8 FPGA on each host. And finally, we have a user level. It's an API that gives oil and gas engineers this ability to use our RTM accelerator easily without spending time to understand what's happening on bottom layers and what is FPGA and how should implement data flow computing. And then we have a shot manager that because our RTM is a combination when it comes to operation in the field, it's a combination of different shots that they send pulses to the ground and gets their data back. And fortunately, these shots don't have any dependency, so we can parallel them and calculate them, compute them in parallel. The shot manager is responsible to divide the shots between different hosts. And then we have PL manager. It is actually FPGA manager, we can call it. Time steps on each shot. We have several time steps to compute the equations, and time steps have true dependency. So what the PL manager does is responsibility to tile the raw data and share it between 8 FPGA that are available on each host. And then it is responsible for doing forward computation, backward computation, and control the cross correlation, and also follow this computing to the next time step. Then we have a stencil core that we talked about it. It's a stencil core of cross stencil core for this case, and we use tiling technique to share the raw data between multiple FPGAs. We have boundary condition manager because in these cases, when you are close to the boundaries of the input matrix, you cannot continue with this stencil. Then you need to get some assumption that get dummy numbers from the boundary, or keep the results from previous steps at that place. So PL has control on the boundary elements and values, and does not let them to be a part of input raw data and send them to BCM. Experimental setup, as we said before, is Amazon EC2 F1, and it's VU9P FPGAs, and we used 16x large because you have 2x large, 4x large, and 16, and we used the biggest one, but we used different FPGA, different numbers of FPGAs. As you see the results here, the bottleneck is DSPs. When we increase the time steps to 14, the DSPs is almost 100, so we cannot continue with that. So if there are another application that we want to run on this FPGA that needs only LUT and block RAMs, it's possible to do that. And then we compare in this table and this graph our system SASIAF with PSM method and DCMA that are state-of-the-art application, and we got 161 compared with 134x speed up when it comes to DCMI, and 126 when it comes to PSM, while PSM has more time steps and we had less, but our frequency was more, and also our window was bigger than PSM. So finally we got better speed up. And at this part of figure 6, scalability on FPGAs, you see that it is almost linear scalable with SASIAF. The conclusion is that AWS is very good for implementing FPGA accelerators, and we got with this system 962x speed up compared with one single CPU. Thanks for listening to this presentation.